Hello viewers, welcome to the KYU Online Materials Lab. In this tutorial we are going to look at the relationship between the dry density and the moisture content of soil. From a brief background, soil is a porous medium consisting of soil solids and water. If a given type is compacted using fixed compaction effort over a range in water contents, a compaction curve of dry density versus moisture content is obtained. This test method covers laboratory compaction method used to determine the relationship between molding water content and dry unit weights of soil. The compaction effort is the amount of energy that is applied to the soil mass. We know that several different methods are used to compact soil in the field, and these include the tamping, kneading, vibration, and the static load compaction. This laboratory will employ the impact compaction method using the type of equipment and methodology developed by R. Proctor in 1933. The compaction curve is a concave downward curve, and at low moisture content, the dry density is relatively low because soil particles are in a poorly organized configuration. So the clay particles adhere to another because they have negative charges on their faces and positive charges on their edges. So as water is added and moisture content increases, the water neutralizes some charges and allows the particles to disperse and assume a more organized orientation. So at some point, the dry density reaches a maximum point, which is called the maximum dry density. If more water is added, the water molecules will fill in between the clay particles and the dry density will decrease. So if the compaction effort increases, the compaction curve will always shift upwards to the left. So the maximum value for the dry density increases and the optimum moisture content decreases. Why do we need to compact our soil? As we all know that mechanical compaction is one of the most common and cost-effective means of stabilizing soil, and the aim here is to reduce the voids in the soil by densifying it. An extremely important task of any geotechnical engineer is the performance and analysis of the field control test to ensure that the compacted fields are meeting the prescribed design specifications. So the design specification usually state the required density as a percentage of the maximum dry density measured in a standard laboratory test. So in general, most engineering properties such as strength, stiffness, resistance to shrinkage, and imperviousness of the soil will improve by increasing the soil density. So that's one of the major aims as to why we need to compact our soil, is to improve its properties. So let's have a brief explanation of the nature of curve that we shall obtain when we plot the dry density and the moisture content. So as we all see, in this curve we have the dry side and the wet side of the optimal moisture content. So optimal moisture content is simply the moisture content that results to the greatest density for a specified compaction effort. So compacting at water contents higher than the optimal moisture content results into dispersed soil structure that is weaker and more ductile, less pervious, soft and more susceptible to shrinkage than soil compacted drier of the optimal moisture content. So the soil compacted lower than the optimal moisture content results into flocculated soil structure that has the opposite characteristics of the soil compacted wet of the optimal moisture content to the same density. Types of compaction equipment. We have the smooth drum rollers. These are best for sands or sandy clay. They offer 100% coverage on the site and they are typically used for finishing operations. We also have the sheep foot roller. They are best for cohesive soils. So they are very poor for cohesionless soils. They compact using a principle of kneading action. And we also have the handheld compactors. These are typically used to compact in tight spaces for small works, usually require small lifts. Finally, let's look at the evaluation of compaction. So engineers in the field will measure the dry density and moisture content and then compare them with specifications provided by the designer. So specifications are usually in the form of a relative compaction and a water content tolerance. For example, the designer may give a specification stating must be greater than 95% of a standard Proctor maximum dry density and within plus or minus 3% of the optimum moisture content. So that will be the work of the contractor to achieve the specifications desired by the consultant or the designer. So relative compaction is equivalent to the field density over the maximum dry density obtained in the lab. So your job as an engineer at the site is to observe the work of a contractor who is performing soil compaction and placing fill material on the site. So how does the contractor know that he or she is doing the right work, or how will the engineer know that the contractor's work is as per the specifications? So that's why we need to evaluate the compaction done. So there are quite a number of ways of obtaining the field densities and field moisture content. So in this tutorial we are just going to list them. Maybe in the next one we shall go in detail of explaining each one of them. So the engineer can use the sand cone method or the nuclear density gauge.